Well, quantum theory may be beautiful, but what use is it? Let's consider the utility of quantum physics. It has a lot of utility, it turns out. Quantum mechanics allows us to predict the properties of atoms and molecules from scratch, from first principles, without appealing to any experiment. We can predict their detailed atomic properties, how much energy it takes to ionize them, what the spectra would be of them. We can take molecules and predict their bond lengths and angles, their dissociation energies, all the details that we would need in chemistry. We can explain spectral features like absorption in infrared and microwave wavelengths. We can do the detail of physical chemistry with rate constants and the enthalpy of reactions. And we can also get into biochemistry, often only in theory, but we can calculate crystal structures in biochemical substances and their binding efficiencies and affinities. These are very detailed properties that biologists, physicists, and chemists need to work, and quantum theory gives you the way to calculate these things, with the caveat that the larger the system, the more difficult these calculations become. Quantum theory is undoubtedly weird, and we'll continue to see how weird it is, but it's an incredibly successful theory. Without quantum mechanics, we could never have designed and built semiconductor devices. Just think of how many semiconductor devices you probably have in your home or your life. Dozens. Computers, cell phones, all sorts of electronics. Lasers would not be possible. So every CD and DVD player, barcode scanners, surgical applications, you also have several lasers in your house, whether you know it or not. And core medical equipment and diagnostic equipment like MRI, magnetic resonance imaging technology, would not exist without quantum theory. Nuclear reactors and nuclear power would not be possible without understanding quantum mechanics, nor would the precision of your GPS navigation device on your phone using atomic clocks be possible without quantum theory. Physicists didn't embrace quantum mechanics because it was cool and the newest thing in the block, and certainly not because it was weird. They actually had trouble with the weirdness. It's simply that it works so well. And in fact, since this is a course on philosophy, the philosophical implications that we're going to get to were actually mostly shelved or ignored. They were studied by some of the influential early physicists. Bohr and Einstein in particular wrestled mightily with philosophical implications of quantum mechanics. But a lot of physicists that came later did not, because it worked so well. And this became pejoratively the shut up and calculate school of quantum physics, where physicists were almost discouraged from delving into its philosophical implications and foundations, and just encouraged to use it as a tool. Here are some examples. The ability of the electron to quantum tunnel through an electrical barrier that we talked about before is the basis of most modern transistors. We don't see tunneling in our everyday lives, of course, because at macroscopic objects and macroscopic energies, an object, even an electron and certainly a ball, can't pass through a wall. It's always repelled. But the wall can be thicker than the quantum wavelength, tunneling becomes improbable. If the wall is thinner than the quantum wavelength for a particle, then the particle can get to the other side, and that's how transistors are actually designed. The quantized character of nuclear spin that we talked about with the Stern-Gerlach experiment is the basis of NMR and MRI technology. The energy difference between the spin-up and spin-down states is what enables NMR spectrometers to differentiate between different types of hydrogen. And these tracers are what are used in the body to diagnose medical conditions. So this is a core medical technology that absolutely depends on quantum theory. Electron tunneling between a tip and a sample is the basis for a scanning tunneling electron microscope, which is just a core diagnostic tool in manufacturing at microscopic scales. And in the more modern world, the measurement theorem enables secure quantum cryptography by guaranteeing that eavesdropping is detectable. So we have learned how to use quantum principles to encode information in quantum systems and produce a key for that code, which we can keep secret from someone. That means that quantum cryptography is far more reliable than any traditional method. And although you don't know it, major banks and financial institutions are now using quantum cryptography techniques to secure your credit card transactions and other aspects of your financial life. Quantum computers are not in everyday use. They're just research tools at the moment. But in the lab, they can perform certain operations incredibly fast and much faster than any of the normal computers we have in our lives. For example, searching an unordered database is a difficult problem in computation. And with a normal computer, you just throw brute force at the problem. Quantum computers can parallelize such a task and do it incredibly fast compared to a normal computer. Also, certain mathematical ideas like factoring large numbers, which, for example, is another tool of cryptography, would bring a large computer pretty much to its knees. But a quantum computer can do these things incredibly well. And that's the end of this topic.